All right, let's dive right into this explainer. Have you ever wondered how long it actually takes to travel through our solar system? I mean, we've all seen the sci-fi movies where a spaceship just kind of zips between planets in a casual afternoon. But I'm talking about the real hard physics of navigating the cosmos with the actual machinery we have today. We are going to explore the fascinating reality of interplanetary travel, and trust me, it is completely different from what you might expect. The distances are absolutely vast, the speeds are mind-boggling, and yet, the journeys take years, sometimes even decades. So why is that? Let's find out.
Do the mental math with me real quick. Intuitively, we think back to the Apollo missions, right? The moon is 384,000 kilometers away, and it took those astronauts about 3 days to get there. So if we point a spacecraft at Mars, our closest planetary neighbor, maybe we assume it takes a week or two. Well, here's the reality. At its closest approach, Mars is literally 146 times further away than the moon. A standard trip actually takes 7 to 9 months. And get this, Mars is the easy one. Once we start looking at the outer planets, we are measuring journeys not in months, but in years and decades.
So here's our flight itinerary for today. First, thinking like the machine. Second, rules of cosmic navigation. Third, the interplanetary paradox. Fourth, the Mars-human bottleneck. Fifth, reaching the giant worlds. And sixth, why the journey matters.
Starting off with Section 1, Thinking like the Machine. The solar system is not a map.
To really understand travel times, we have to completely stop looking at the solar system like a fixed map on a piece of paper. It's a giant machine of constantly moving parts. Planets travel in stretched ovals called ellipses, meaning the distance between any two planets is constantly changing. Because of this, pointing a rocket directly at a planet is almost always wrong. By the time you get there, the planet has moved. Instead, we use what's called a Hohmann transfer. It's a flight path shaped like half an ellipse. You basically leave Earth's orbit and gracefully coast to meet your target planet's orbit at exactly the right moment. It is the single most fuel-efficient route we know how to fly. But the ultimate cost of this incredible efficiency? It's a massive amount of time.
Think of spaceflight like throwing a deep pass in football. You don't aim at where the receiver is standing, you aim at where they will be. This requires incredibly precise predictive math. Your launch window determines exactly where you start and where you need to throw that cosmic pass to ensure your spacecraft and the target planet arrive at the exact same spot at the exact same time.
Moving right along to Section 2, Rules of Cosmic Navigation, and specifically, the braking problem.
Okay, so the absolute hardest rule of cosmic navigation is a plot twist that dictates basically everything, the braking problem. Accelerating in space is actually pretty straightforward. Once you're moving, there's no friction, so you just keep moving. The really hard part, the limiting factor for almost every mission, is arriving at a speed low enough to actually be captured by a planet's gravity so you can orbit or land. And in space, hitting the brakes costs exactly as much propellant as accelerating. Just think about that for a second. Every single kilogram of braking propellant you carry must first be lifted off Earth, accelerated across hundreds of millions of kilometers, and then finally burned against your own momentum just to slow you down. The required mass grows exponentially.
Because carrying all that braking fuel is often literally impossible, engineers use the closest thing spaceflight has to a free lunch, the gravity assist. Though fair warning, it takes years to get served. By swinging a spacecraft super close to a planet, it can borrow a fraction of that planet's orbital energy. The spacecraft can then exit the other side going faster or slower without burning a single gram of extra propellant. The legendary Voyager 2 actually chained 4 of these gravity assists together. Without them, reaching Neptune with current propulsion would have required more propellant than any rocket ever built could even lift off the ground.
Let's look at Section 3, the interplanetary paradox. Mercury and Venus. So let's see how these physics rules build a massive counterintuitive paradox right in our own cosmic backyard. 6.5 years, that is how long it took the MESSENGER probe to reach Mercury. Mercury is the closest planet to the Sun, yet it is somehow one of the most difficult places in the entire solar system to reach. You see, the solar system doesn't grade on proximity. Getting to Mercury is a problem of energy. Because it sits so incredibly deep in the Sun's gravitational well, a spacecraft heading inward from Earth is constantly being accelerated by the Sun's massive gravity. To actually stop at Mercury and not blow straight past it into the Sun, a probe has to shed an enormous amount of speed. MESSENGER needed 7 gravity assists, threading through Earth and Venus just to slow down enough over 6.5 agonizing years to finally be captured into orbit.
Now, Venus tells a really similar story about the sheer cost of braking, showing these wild variances in transit times. Check this out.
Mariner 2 got there in just 110 days doing a fast flyby. It didn't need to stop. But Pioneer Venus took almost double that time, 198 days. Why? Because a slower approach is way more fuel efficient. The variance reflects exactly how much speed you need to shed upon arrival. If you want a fast approach, you need way more braking fuel. And if you don't have the mass budget for that fuel, well, you have to take the slow, extremely long scenic route.
And what actually awaits us after that long, super careful transit? On Venus, the answer is a blisteringly hostile environment. The Soviet Venera landers are the only spacecraft to ever transmit images from the surface, and the most durable ones survive for exactly 127 minutes. That's it. Venus has a surface temperature of 465 degrees Celsius, which is hotter than Mercury, by the way, under a crushing atmosphere 92 times Earth's pressure, complete with thick clouds of sulfuric acid. The heat, pressure, and chemical corrosion made surviving any longer structurally impossible with 1980s engineering. It's a pretty stark reminder of the incredibly extreme conditions we spend years trying to safely reach.
Which brings us to Section 4, the Mars-human bottleneck, shifting from probes to people.
Mars is where our narrative shifts from purely robotic probes to the intense, complex engineering challenge of keeping humans alive. But we're facing a massive bottleneck here. The standard Hohmann transfer using chemical rockets takes 7 to 9 months one way. That duration introduces real, completely unresolved biological hazards for a human crew. When you're outside Earth's protective magnetic field, a 2-year Mars mission exposes crews to roughly 0.66 sieverts of cosmic radiation, which completely exceeds the career lifetime limit for NASA astronauts. Add to that bone density degradation and cardiovascular decline from microgravity. Now, these are absolutely solvable engineering problems, but they're not solved quite yet.
The central planning problem for crewed Mars missions isn't actually just the life support, it's the speed. What shortens the trip and saves human lives is higher thrust propulsion. Current chemical propulsion totally locks us into that 7 to 9 month transit. But nuclear thermal propulsion, which uses a fission reactor to heat hydrogen propellant, could theoretically cut that transit time in half, down to roughly 3 to 4 months. The catch? The technology exists in prototype form, but it has not been flight tested in space. Closing that gap is arguably the absolute most important investment needed for human spaceflight today.
All right, Section 5, reaching the giant worlds, Jupiter, Saturn, and beyond.
Out beyond Mars, the scale of everything changes completely. Jupiter perfectly highlights this braking problem we've been talking about. Pioneer 10 did a direct flyby and reached Jupiter in just 21 months. It was moving super fast. But remember, it didn't stop. The Galileo orbiter, on the other hand, took nearly 6 years to reach orbit. Why? Because arriving at Jupiter too fast means flying straight past it into deep space. Galileo literally had to loop through a Venus flyby and 2 Earth flybys just to carefully arrive at precisely the right velocity to be captured. The upcoming Europa Clipper? It's taking 5.5 years. Stopping at the gas giants is a massive test of patience.
Saturn pushes that patience even further, but I promise you the rewards are incredible. The Cassini spacecraft spent 7 agonizing years in transit, threading gravity assists through Venus, Earth, and Jupiter, just to arrive at the exact speed required to finally enter Saturn orbit. But that 7-year investment bought us 13 unbelievable years of studying Saturn, its rings, and fascinating moons like Titan and Enceladus. It basically proved that the long, highly complex journey was worth every single year.
Beyond Saturn, we have barely even scratched the surface. We have visited the ice giants Uranus and Neptune exactly once, and we only pulled that off because Voyager 2 exploited a super rare planetary alignment that repeats approximately every 176 years. It is honestly awe-inspiring to think about the vast timescales required by orbital mechanics. We just don't have that alignment right now. So the leading candidate for a future dedicated Uranus orbiter anticipates a cruise time of roughly 13 years just to get there. That isn't a failure of human planning, it's just an honest accounting of what orbital mechanics absolutely demands when we venture this far out into the dark.
And then, of course, there's Pluto. The New Horizons spacecraft took 9.5 years to reach Pluto, flying at a peak speed of around 57,600 kilometers per hour. But it was strictly a flyby mission. So why not stop? Well, to actually break and enter orbit around Pluto, New Horizons would have required additional propellant mass equal to approximately 4 times its entire launch mass. The fuel requirements are just mind-boggling. And that's exactly why right now, missions to the extreme outer edges of our solar system are pre-programmed as flybys.
Finally, Section 6, why the journey matters. Pointless versus profound.
With decades of travel time, you might seriously wonder if this slow pace makes the whole effort kind of pointless. But I assure you, it is profound. Every single mission that has reached another world has returned knowledge that completely changed what we believed about our solar system. None of these results required the journey to be fast. They just required the journey to be made. We found active nitrogen glaciers on Pluto, a massive subsurface liquid ocean on Europa that literally contains more water than Earth, the moon Enceladus actively venting organic material into space, and we've studied Venus's runaway greenhouse effect. These slow, robotic emissaries have fundamentally rewritten our textbooks.
As the legendary Carl Sagan observed, somewhere, something incredible is waiting to be known. He wasn't just being poetic there, he was making a direct prediction about these specific, bounded, reachable worlds we've discussed today. The truly profound questions, like whether life exists elsewhere, they aren't going to be answered by philosophy. They're going to be answered by a probe descending through Europa's ice or a lander analyzing a plume from Enceladus. Yes, those missions are years or even decades away, but that is the very definition of a long-term project absolutely worth having.
So, the next time you look up at the night sky and see the steady, non-flickering light of a planet, I want you to remember the immense, years-long journey it takes just to get a probe there. We are really only at the very beginning of understanding our own cosmic neighborhood. The slow, patient accumulation of knowledge over decades has been simply extraordinary. So my question to you is, considering the massive distances and the brilliant engineering required just to hit the brakes, where will we go next? Thanks so much for joining me on this explainer. Keep your curiosity alive, and I'll see you next time.